Welcome to Operations Research. In this linear programming problem module, at the end of this video, you should be able to understand the concept of degeneracy in LPP, that is linear programming problem, and you should be able to solve a degenerated problem or degenerated linear programming problem by using simplex method. Now, before we go to solve an actual problem, let us understand what is exactly degeneracy in LPP. The literal meaning of degeneracy is that fallen below a normal or desired level. So there is some kind of an lacuna, some kind of an discrepancy in linear programming problem that avoids or that makes us difficult to get the final solution or optimum solution. Degeneracy occurs in LPP when basic variables acquires zero value. Now in a LPP we call those variables as basic variables which are greater than 0, but if any of the basic variables become 0, then we call that this particular linear programming problem is degenerated. Now it is manifested by, in the final solution, either the number of basic variables is not equal to number of constraint. So that is one of the condition that can occur, or in some cases in final solution this basic variables become 0. Now in simplex table, when there is a tie between the replacement ratio of the two variables for a minimum positive value, so this is the kind of a manifestation of this degeneracy in the simplex table. So while solving the simplex table, we come across this tie for replacement ratio. So you get the same minimum positive value of replacement ratio which we use for deciding the leaving variable or departing variable. So let us understand all these things with the help of one example. Here is our problem statement. Now we are considering we want to maximize some objective function. So maximize z is equal to 3x plus 9y. So x and y are our decision variables, and we want to maximize this objective function, which is subjected to two constraints. So x plus 4y is less than or equal to 8 and x plus 2y is less than or equal to 8, and this is a non-negativity constraint, which means that the values of x and y, that is the decision variables, can not have any negative value. They can be 0 or greater than 0. Now let us move to solve this problem. Now these are the steps which we are going to use for solving the linear programming problem with the simplex method. The first step would be to convert the LPP to a standard form that we are going to see. Second step would be to form the initial simplex table or initial simplex table. The third step would be to establish an initial feasible solution. Next step is to locate the scope for improvement. Then we will identify an entering variable and departing variable, and then we are going to iterate these steps, specifically these two steps, until we get the optimum solution. So these are the kind of an summary or these are the steps which are involved for solving the LPP with the help of simplex method. Let us put all these steps in a flow chart so that we can understand things much better. So these are the first three steps, that is convert the LPP to a standard form, create the initial table, establish the initial feasible solution, and then we have to locate the scope for improvement, which is done by computing Cj minus Zj. Now what exactly this Cj and Zj and how to compute all these things, we will see with the help of one example. Now once we know that there is a scope for improvement which is evaluated by this quantity as Cj minus Zj. So if Cj minus Zj has any positive value for any variable, then we say that we have a scope for improving the current solution, right? And then we identify the entering variable, departing variable, and update the table, and we go back to this computing the Cj minus Zj for the new improved table. Once we reach a point where Cj minus Zj values are 0 or negative, we can say that the optimum solution is reached. Remember that all these steps are valid when the problem is of an maximization type of a problem. Let us now move and see how to solve this problem. Now the first step would be to convert the given linear programming problem, that is objective function and constraint, to a standard form. So the first step would be to identify or add the slack, surplus and artificial variables. Now if the constraint is of less than or equal to type, we add the slack variable. If the constraint is of greater than or equal to type, we subtract the surplus variable and we also add on one artificial variable. And if the constraint is of equal to type, then we add only artificial variable. Now you just remember this table because we are going to use this logic to make a standard form. Let us add these variables to our constraint and objective function. Now we know that this is our objective function and we have two decision variables, that is x and y, and we are going to modify these constraint. So we are going to eliminate this less than or equal to sign, so it is a kind of an inequality, and to solve this problem we need equality, right? So we are going to remove this less than or equal to sign by adding slack variables to make it in a standard form. Now if we pull the logic that we have just learned in last slide, we have less than or equal to type of constraint. So both the constraints are of less than or equal to type, so we are going to add the slack variables. So we are going to add one slack variable over here and another slack variable over here. So we will call them as an S1 and S2. Okay, now this right now we are not going to update this objective function, so I am writing it in the same way, but I will be updating this constraint by adding the slack variable, that is S1 for the first constraint and S2 for the second constraint, and I will eliminate this less than or equal to type of sign with the equality sign. So we have done, like, we have removed the inequalities from the constraint, and now we need to update the we need to update the objective function and constraint so that we will get the standard form. Now this is the two things, that is objective function and these are the constraint having equal sign. We have to take it as an input, and now you have to look for this table. Now we have a constraint of less than or equal to type, right? So its coefficient in the constraint will be +1. So for this first constraint we have taken it as plus S1, and for second constraint we have taken it as an plus S2, but its coefficient in the objective function is going to be 0. So we have to add these two slack variables in the objective function with 0 coefficient. Now we should be knowing that slack variables are used, or they signify the unused or idle resources. So let us add this S1 and S2 in the objective function with 0 coefficient. So our objective function will be modified as 3x plus 9y plus 0 into S1 plus 0 into S2. Now we have selected this coefficient of slack variable as 0 for this objective function because here Z represents the profit and we want to maximize that profit, as the slack variables do not contribute anything in the profit, so we have marked them as a 0 coefficient in the objective function. Now let us modify this constraint little bit so that it will be easy for us to fill up the simplex table. So what I'm going to do, I'm going to add this. The initial part is same, that is x plus 4y plus s1, and I'm going to add this 0 into s2. So this is going to be the 0 thing, but I need this to make things more simple. So we want the different variables, so we have 4 variables over here now: x, y, s1 and s2 in a same order, that is x, y, s1 and s2, and I have written 0 coefficient for this S2 in the first constraint, and the remaining things are same. In a similar fashion, second constraint can be modified like this. So x plus 2y plus 0 s1, because this constraint do not have s1, so I am just added the s1 variable with 0 coefficient, and everything is same. Now this is the standard form for the simplex table, and with this form we will go and fill up the simplex table to get the initial feasible solution. Now we need to prepare this blank simplex table, and we need to fill all these objective function coefficients and constraint coefficient in this table, and then we need to solve this simplex table. So the Cj represents the coefficient of variable in the objective function. So in objective function we have four variables x, y, s1 and s2. X and y are decision variables, s1 and s2 are the slack variables, and the Cj represents their coefficient in the objective function. So let us fill this table step by step. So the first step would be to fill up all the object variables in this objective function. So we have four variables, so I am writing four variables over here. So here I will be writing as x, y, s1 and s2, and I will be writing their coefficients as 3, 9, 0, 0. Then we have to identify the basic variables. Now this is the initial table, and at initial point we assume that all the decision variables are 0, and we call it as an zero production point or no production point, where the values of decision variables, that is used resources, are 0. So there will not be any values associated with x and y, and all the values will be associated with s1 and s2. So we are going to write down this basic variables, two basic variables in this column, and the coefficient of this s1 and s2 in the objective function is 0. Now next step is to put the values in these rows. So we have two rows and we have two constraints. So this particular column, now this column 3 will be associated with this variable x, this column 4 will be associated with y, this 5 column will be associated with s1, and 6th column will be associated with s2. This right hand side indicates the right hand side of the constraint, and replacement ratio that we are going to calculate. Zj represent the profit, and Cj minus Zj, that is the subtraction of the Cj minus whatever value will come in Zj, will be written over here. Now we will add this first constraint in this first row, so that will becomes the coefficient of this x is 1, coefficient of y is 4, coefficient of s1 is 1, and coefficient of s2 is 0, and right hand side is 8. So this will be 1, 4, 1, 0, 8, and for the second constraint I have also written the coefficient in the respective places, so that is 1, 2, 0, 1, 4. Next step is to calculate the value of Z, that is the profit, for each of the column, and that is given by this 0 into 1 plus 0 into 1, that is 0 for this x. For y it will be 0 into 4 plus 0 into 2, again it will be 0. For this s1 it would be 0 into 1 plus 0 into 1 will give the value of 0. The next step would be to get the value of the Cj minus Zj, that is 3 minus 0 will be 3. 9 minus 0 will be 9, and 0 minus 0 will be 0, 0 minus 0 will be 0. So we got these values of Cj minus Zj. Now if you look at this point, you can notice that we have a positive value of this Cj minus Zj with us, which indicates that we have a scope for improvement. Now among all the Cj minus Zj value, the corresponding value of this y is maximum positive value, that is 9. So we can say that y is our entering variable. So y will become our basic variable and it is going to replace any of these two variables, that is s1 and s2. Now to evaluate the departing variable or leaving variable, we have to evaluate the replacement ratio. Before that, let us call this y as key column. Now the replacement ratio will be evaluated by solution RSH value, that is 8 divided by corresponding element in the key column. So 8 divided by 4 will give me the value of 2. Similarly, 4 divided by 2 will give me the value of 2 again. Now you can note that we have a similar value of this replacement ratio. Now usually we select the minimum positive value of this replacement ratio as our departing variable. But here is a tie between these two values and that is why this problem is degenerated. To resolve this degeneracy, we have to find out a new replacement ratio so that we can select the departing variable. New replacement ratio is given by this quantity called as an S1 divided by Y. That is, S1 is the first identity variable of this identity matrix and Y is your entering variable. So for each row we will evaluate the value of S1 divided by Y. So it is given by 1 divided by 4, that will give me the value of 1 by 4. For the second row it will be 0 divided by 2, that will give me the value of replacement ratio or new replacement ratio as 0. Now among these two new replacement value, we have to select the minimum value and that is 0 and which is corresponding to this row S2. So we can say that S2 is the departing variable and let us call it as a key row. So this will be your key row and the element at the intersection of this key row and key column, we are going to call it as a key element. Now all these things are required for updating this simplex table for the next iteration and that we are going to call as a first iteration. Now this is our old simplex table and this is the key row and this is the non-key row. We also evaluated that y is our entering variable and s2 is our departing variable. Now we need to prepare a table which we are going to call it as an iteration 1 and we are going to update this table. Only change will be that this x, y, s1, s2 will be there. Only instead of this s2 in the basic variable list, we are going to put y because y was our entering variable and it is going to take the place of this s2 because s2 was the leaving variable. Now there are two types of rows in this new table. One is reduced row and other is replaced row. The row corresponding to the key row, we are going to call it as a reduced row, and the row which is not corresponding to this key row, we are going to call it as a replaced row. This reduced row elements are given by this formula. So new element in the reduced row will be corresponding element in the key row divided by the key element, and we know that the key element is 2. So for this position, element will be given by corresponding element in key row which is 1 divided by key element 2, so that is 1 by 2. In the same way, other elements can be evaluated. So for example, this 1 is got by 2, that is element in the key row divided by the key element which is the same, that is 2 by 2, 1. And now it is time to get the elements for this replaced row, for which we are going to use this formula. So element in the replaced row at this position will be given by element in the old row. So element in the old row, that is 1, minus intersecting element of the old row, that is 4. So what is intersecting element? So it is corresponding to this key column and corresponding to the row, which is 4, into corresponding element in the reduced key row, and this is the reduced key row that we have evaluated. So corresponding to this cell is 1 by 2. So this element is given by element in the old row for the same position, which is 1 minus in bracket intersecting element is 4, which is corresponding to this key column, and corresponding element in the reduced key row is 1 by 2. So if we put all these values in this formula, we get the value of minus 1. Similarly, we can evaluate the values for these remaining positions. Now once we get all these values, it is time to evaluate the value of z and cj minus zj. We know that the value of z is evaluated by multiplying these two elements. So 0 into minus 1 plus 9 into 1 by 2, which is equal to 9 by 2. In the same way, we can evaluate the values for these remaining columns. So here it is 0 into minus 2 plus 9 into 1 by 2, which is equal to 9 by 2. Next thing is to evaluate the value of Cj minus Zj. So the Cj value is 3 minus 9 by 2 is equal to minus 3 by 2. In a similar way, we can evaluate values for the remaining columns. Now here you can note that all the values of Cj minus Zj are either 0 or negative, and thus we can see that this is the optimum solution. And the values of the decision variables are x will be 0, y will be 2, and value of z will be 18. As we have discussed initially, we are getting one of the basic variable or one of the decision variable as 0, and that is why the problem is degenerated. And y value we are getting 2, for the z value 18. So this is the final solution and we can stop at this point. Thank you for watching this video. Also subscribe this channel. PDF solution of this example is available and the link is available in the description section. Thank you.